OK, good. OK, so we have curly H, the Hamiltonian of the universe, and we have that the state of the universe is an eigenstate of the Hamiltonian of the universe. So that effectively we have removed the usual time evolution because this is a stationary state. So overall, there's no time evolution at the level of the universe. And now the key is, the problem is how do we recover the usual time evolution that we are familiar with. And so Page-Wootters, as I said, divide the universe into two subsystems. One is, let's say, the system of interest, and the other one acts as a clock for the first one. In their paper, and usually people dealing with Page-Wootters assume that the clock and the system are not interacting. This is an idealization, but it's useful to get the nice results at the beginning, but then we'll see how to modify this assumption. And last, they assume that the clock has an observable t, which is canonically conjugated to its Hamiltonian. So HC here is the Hamiltonian of the clock. And in this case, we usually talk about ideal clocks. So we are working with ideal clocks when we have this kind of like algebra for the clock. And from this time operator here, so from this t operator here, we can find these improper eigenstates. And this is an idealized case, and people have shown how to modify this assumption. But for now, all the results are valid if you consider this idealized case. OK, so I'm just going to teach you how to do Page-Wootters. So let's start with the state of the universe, which is an eigenstate of the Hamiltonian of the universe. And let's insert an identity written in this way. So we use the completeness of the eigenstate of the t operator of the clock. We insert it like this. We bring in t and we multiply to, we take this partial inner product, t psi. This is going to be our psi labeled by the parameter t. And then t just goes here. And so in general, we can write any state of the universe. We just decompose it in this basis, let's say. So we just insert this identity like this, and we write it like that. Now, so that's the we use the algebra of the clock here. Now we find another equation by applying the stationarity constraint. So we start with psi, and now we apply this unitary here, e to the minus I Hamiltonian of the universe theta. We know that psi is an eigenstate of H of the universe, so this is just going to give us 1. So that's why I wrote this equation here. And in the second equation, I made this explicit, how this operator acts on psi. And we separate the two Hamiltonians of the system and clock. And then we have this side on the system side, like this operator on the system side. And then e to the minus IHC theta acts on t in this way. So it's just like a time translation on the t eigenstates of a clock. Now, by equating these two equations, we find that this psi t, so the states of a system labeled by t, evolved have this property, so that they're related to the initial state by these unitary transformations here. So what does it mean? Now, this is all maths, but what does it mean? It means that if we consider the state of a system relative to the clock being in a state t, which is given by this expression, this is nothing else but than psi t. And we've seen that it evolves this way. So what does it mean? That the state of a system relative to the clock being at time t, so this collection of states evolves in the usual Schrödinger way. So we recovered the usual Schrödinger evolution on the system side, even if the whole universe is stationary. So we have a whole stationary universe, and by these simple relations, we find that relative to the clock, we can find the usual Schrödinger equation, like usual Schrödinger evolution on the system side. And that's Page-Wootters. And here it's a nice picture from Giovannetti and others where that they used to explain this model. And basically, this box here is the state of the universe, and is made up of this collection of all these states here. And by measuring time on the clock means like just projecting or like slicing the state of the universe in this way, and we get this psi of t. And now if you compare this psi of t with other psi of t's, we see that they are related in this way. So that one slice evolves with a usual like Schrodinger wave from the previous one, and so on. OK, and this is the usual Page-Wootters stuff. So now, I want to comment on this point, which is sometimes. Before that, is it crucial to have a zero here in the? Is it crucial that we have a zero energy eigenstate of Hamiltonian of the universe? So usually we consider 0 here because this comes from a Wheeler-DeWitt equation. But is it really crucial? Can we relax this assumption? And the answer here is yes. OK, we do the same thing as before, just that now we impose the stationarity in this way. And basically the same procedure as before. And then we find that the state of a system evolves in this way. So we have the previous part, e to the minus IHST. And now we have this epsilon, which is the eigenvalue of the state of a universe. And basically, we see that this epsilon here is just a trivial energy shift. And so at the level of the system, this is not observable. It doesn't really change the dynamics. It amounts to a global phase change, which is not observable. Great. So yeah, here's a question, like why should we prefer one eigenvalue over another? And here we can't really see why. I mean, they give the same predictions on the system side. But later we'll see how this changes when we add system and clock interactions. Right. Can we relax the assumptions even more? So can we consider mixed states of a universe instead of pure states of a universe? And I'm going to show you, but yes, you can do that. In general, now we write the stationarity constraint in this way. So here R is the state of a universe, and it commutes with the Hamiltonian of a universe. So in this way, it's stationary. And someone might be puzzled by mixed states of a universe. What does it mean of the universe, that the universe is in a mixed state? But without getting into debates about the state of a whole universe, which probably, I mean, to me, it's more likely that it's pure. But let's consider this example where we have a bigger universe here. We have our usual system here and clock here. And now we have a first system, which is inaccessible to this couple of system and clock. Then one might describe what is going on here. So we have this constraint on so this Hamiltonian of a universe, just the sum of the Hamiltonian of system and clock plus the Hamiltonian of this inaccessible system here. This universe is in a stationary state like this. And now we might consider just the state of a system and clock by neglecting the inaccessible system. And we might come up with some sort of partial trace here, which could do the job and tell you what is the state of a system and clock, given that I don't have access to this inaccessible system here. And if I do this operation here, then I recover this general density matrix of system and clock, which will commute with the Hamiltonian of a system and clock. And in general, it's not a pure state. So in this case, yeah, by neglecting a third inaccessible system, we have a mixed state of system and clock, which is still stationary, but yeah, we lost the purity of the state. So that's why I think it's useful to also consider this scenario, because we want to deal with every kind of system. And in some sense here, we're doing Page-Wootters twice. We're doing one on the whole universe, and then one on this subsystem of a universe here. OK, so can we work with mixed states?
Sorry, can I something like on the previous slide you had this, that you don't constrain yourself with a zero charge.
Yeah.
So you could also think about mixedness in different charges, of not having a and the clock, but nevertheless being the state in a classical mixture of subspaces.
Yeah.
And I mean, this is also possible. Considering my second question, you said that epsilon is not observable, so would I even know whether I'm in a mixed state or pure in that case?
Yeah. At this stage, you wouldn't know. If there's no system and clock interactions, you wouldn't know. Yeah, and it's correct. You don't have to trace out things. You can just like start from a statistical mixture of different energy eigenspaces of a universe, and you still have a mixed state. And I'm going to show you that it gives you the same predictions on the system side. OK, great. So yeah, can we do the things with mixed states? Yes. So how does it work? Well, so the state of a universe commutes with the Hamiltonian of a universe. So we can write the state of a universe in this way. So as this combination of these energy eigenstates of a universe. And here, K denotes like different energy levels of a Hamiltonian of a universe. And dk is just the generality label for each energy eigenvalue of the universe. OK, so in general, then, like we insert as before these identities expressed like as the integral dt of t cat t bra. So that's the composition of the identity. We insert one on the left and one on the right. And this is the expression that you get. OK, and now we need to define a relative state, so the state of a system relative to the clock being in t. And we define it like this, where this is just this projector on the t eigenstates of a clock. And I just use this notation because it's a bit more compact. But it's basically the same operation as before, just for now we have a density matrix, so we're acting on both sides with this t. And here is just a normalization factor. OK, you do that. You calculate the relative state for this state here, and you get this expression for the state of a system at time t. Now, each of these states, so each of these states here is the solution that we've seen before, but just with different energy eigenvalues of the Hamiltonian of a universe. So now, each of these states of a system will evolve in this way. So usual Schrödinger evolution, and the energy shift. If you have this on the left and this on the right, these energy shifts cancel out. And the result is that this is the evolution of the state of your system. So the state of a system is still going to evolve in the usual Schrödinger way, in the sense, yeah, it will obey the usual Schrödinger equation. And so we've seen that even with mixed states of a universe, the conclusions don't change. We cannot really tell if we are in a mixed state of a universe or in a pure state of a universe. The evolution on the system side is going to be identical. Great. Before moving on, I just want to comment a bit on entanglement, because usually what is said is that in the Page-Wootters construction, entanglement emerges from time. What does it mean, and is it true? Well, for pure states of a universe, we've seen that we can write them like this. And we notice here that this state is entangled. I mean, in general, this is an entangled state. And here I'm talking on the kinematical Hilbert space, so I'm not entering in other discussions about the physical Hilbert space. But I'm just saying on the kinematical Hilbert space, this state in general is entangled. When is this state separable? I mean, it is separable if and only if. I mean, basically, we have one term in the integral. Like, we can take this thing out, and we have a separable state. So basically, what happens is that the state of the universe is separable only if all these psi of t's are proportional to each other, which means basically that there's no time evolution on the system. So basically, this is gonna psi of t is gonna be psi of 0 apart from a phase maybe, and this means that the state of a system is gonna be fixed apart from a global phase which is not observable. So the answer is yes. In this picture, time emerges, so like a non-trivial time evolution, which means like that the system is gonna be in at least two different states at some point, if and only if the state of universe is entangled on the kinematical Hilbert space. So it's quite crucial that in the with pure states we have entanglement. Sorry. Great, and so yeah, time in some sense emerges from the purely quantum correlations between system and clock in this picture. And I'm going to show you later why that is not always the case. Actually, here I'm going to mention for mixed states of a universe, is it still the case? Do we need that the state of a universe has to be entangled with respect to system and clock? And now the answer is no. We can encode the usual time evolution on the system in the classical correlations between system and clock. An example of such state is this state, which is a separable state. Actually, this is a quantum classical state. And if you take the relative state, so if you project on the time t, you're going to see that this psi t evolve in the usual way. So you basically recover the usual Schrödinger evolution, even from a separable but mixed state of a universe. So here's the difference. Like if you allow the state of a universe to be mixed, then you can also have separable states of a universe that give you the usual time evolution. Okay. Here I put forward a question about the agreement with classical rational approaches to time, because in some sense here we see that we're encoding the time evolution in the classical correlations with the clock. We're only accessing, let's say, one observable of the clock, so one quantum degree of freedom. So we're not going into the energy eigenstates. And so is this the way of unifying Page-Wootters with some classical relational approaches to time? So my understanding of classical non-relativistic approaches to time is that you need to work with how do you say, density of states in phase space. And my question here is this the way of connecting Page-Wootters to these classical models, classical approaches to time? This is an open question. I don't have much more to say about this. But there's a catch, and the catch is that to have these kind of states, we need to work on multiple eigenspaces of the Hamiltonian of the universe. So if you remember, this is the way we express the state of a universe. We need to work on multiple energy eigenvalues to come up with these states here. And this is going to be important later. But for now, with time from entanglement, so to answer the question, time from entanglement, not really, not even on the kinematical Hilbert space, if we allow the state of the universe to be a mixed state. Yeah?
Really, this stays the same. I mean, you put R and R, but isn't it below you have some kind of off-diagonal elements in T?
Yeah. That's a good question. Yeah, here basically you have to go and sum over all the, I mean, you need to get a continuous spectra of eigenvalues of a universe, and then you can get a Dirac delta of t minus t prime, and then it kills you of the off-diagonal elements. Yeah. Yeah, there's some conditions on how you can recover that, yeah.
Another question is, for the state above that you wrote as an integral over mixed states, do you still recover like a Schrödinger-like evolution for the psi, or?
Yes, yes. Yeah, sorry, I haven't written here, but this is just e to the minus IH ST on psi 0, yeah. So by just like singling out a specific t state, you're gonna get the common, like usual Schrödinger evolution. Okay, great. Now, this is to conclude like exploration, like variations on Page-Wootters, but without system clock interactions. Now let's consider system clock interactions. Yeah, before doing that, I'm just gonna introduce a notation that is gonna be, it's gonna make it easy for us to work with the system clock interactions later. So let me define this derivative now with respect to a time operator. let's just work heuristically here, and let's not get involved into the mathematical details. But it's going to turn out to be quite convenient way to quite convenient notation. So I'm just going to define it like this. So basically, for these bipartite states like a system and clock, I'm just going to project on t, take this derivative here, and then integrate over all time states t with t here. So I mean, this is just a definition, but then what it turns out to be that it's that you can show that this time derivative, or maybe there's a I here, not here, but anyway, the action of this time operator derivative on psi is just the action of the Hamiltonian of the clock of psi. So it's just a compact notation of expressing for expressing this action of Hamiltonian of the clock on psi. For now, it's just like a notation. Like it's useful because now we can quickly do Page-Wootters in the sense that this is our constraint equation. We put in the expression for the Hamiltonian of the universe, and we rearrange the terms, and we have hc on the left here, and the h minus epsilon on the right, and we use this expression for the time derivative, so we get time derivative here equals to this thing here, and now this is basically a operatorial Schrodinger equation. So it's just the usual Schrodinger equation, just that now we have t hats here instead of a usual t. How do we get the usual Schrodinger equation? We sandwich with this t here, so we take this partial inner product, and we get the Schrodinger equation, the usual Schrodinger equation. So it's just like a convenient notation. And this, I'm going to do the same for derivatives of operators with respect to the time operator t. I'm going to define it like that. So this is a very simple case of a derivative of an operator with respect to another operator, where I basically take a variation along the identity, or like along t, like the diagonal of t. Again, you can prove that this thing is equal to this thing here. So it's just the commutator of the Hamiltonian of the clock with the operator a. And again, we have the constraint equation for the general mixed state. We insert this expression here. And we insert the expression for the Hamiltonian of the universe and this thing here, and we get the dr on dt is this thing. We take this partial trace with these time projectors as before, and we get the von Neumann-Liouville equation for the state of a system. Anyway, it's just convenient notation now. But, and let me show you how it's useful for system clock interactions. So first of all, why do we need a system clock interaction? So we have this Page-Wootters approach provides an insightful way of like how to approach time in quantum theory, or like one potential solution to the problem of time in quantum theory. It's insightful because it tells you how you should treat time, or like you should recover it from correlations between systems. But it's not the most general model. There's still many doubts, and I'm just going to mention two. One is that we are assuming that the clock is ideal, and that's a very high idealization, and there's people working on how to go beyond this approximation. Another thing is that in general, a realistic model should take into account interactions between the system and the clock. Because in general, we can have interactions between system and clock, which are not considered in the original Page-Wootters approach. Okay, so let me do that. So let me consider system and clock, and let's add this interaction bit here, this v hat. How do our conclusions change? Well, now I'm going to use the notation I introduced before to show you a way to solve the Page-Wootters model for any kind of interaction. And I'm just going to tell you to get your constraint. So for any constraint you have, get this constraint. And now you move all the HCs on the right and all the T's on the left. You apply the constraint on the state of the universe, usual thing. And you use the definition of a time operator derivative I introduced before. And then you take the partial linear product with time eigenstates. So let me give you an example. We start from this constraint here. So we have h of a system, Hamiltonian of a system, plus Hamiltonian of a clock. And now I've added an interaction bit of this form. So it's just like an operator on the system, tensor the time operator on the clock. And so let's just apply the steps as before. So now we don't need to move things around here. We just apply the constraint and insert the HC, so the definition of d on dt in terms of HC that we've seen before. And we get this thing here. Now we just sandwich with the t from the left and rearrange the terms. And we're going to have a time derivative. Here should be, sorry, without the hat. H of a system plus x on the system, and this t parameter now times the state of a system. So basically, we get a new equation for the state of a system. And it's the Hamiltonian now of the system is hs plus this extra term here, which depends on time. And basically you solve. Now usually there's no problem. If this is Hermitian, you have an Hermitian operator, you integrate, you find the solution to your for the state of your system. And also it tells you how to deal with, like, how to treat time-dependent Hamiltonians in Page-Wootters. You just insert things that depend on the time operator here, and then you're going to get effectively a time-dependent Hamiltonian, effective Hamiltonian for your system. So this was very easy. OK. Another example, a bit more involved. Now, instead of t, we have the Hamiltonian of the clock here. So what do? We do a bit of moving things around. So we have hs. So we apply the constraint. We have hs and minus. Now we gather hc on the right. And we have 1 plus x on the left. hc is minus I, the time operator derivative. We move this to the right. And now, if the inverse of this exists, we act with inverse on the left, from the left. And basically, we get this equation. Then we sandwich with t, and we get this equation for the states of a system. So now this is a very easy way to solve the model with this generic kind of interaction. And it also tells us some interesting bits. For example, if this x doesn't commute with the Hamiltonian of a system, this in general is not Hermitian. And now we're going to have problems. So we're going to have, for example, a non-unitary dynamics on the system side. And this was explored also in this paper here. And we're already seeing some of the problems that emerge when with generic types of interaction between system and clock. For some kinds of interactions, we don't have a unitary dynamics on the system side. Which is a problem. And again, I'm going to give you another final example. Now I have an x operator on a system here in the interaction, and now I have a Hamiltonian of the clock squared. Same procedure as before, just that now we get also second time operator derivatives. We sandwich with t, and we get this equation for the states of a system. And now, I mean, now the problem is like, is this does this give a unitary evolution for the system? I'm not going to deal with this now, but what I'm just saying that in this way we can immediately get with this notation and with this trick we can immediately get the equation of motion, the equation for the state of a system, and then from that we just need to determine if this equation gives us a unitary dynamics or not. But yeah, that's a very convenient way to deal with this constraint. So given that, and given the problem we've seen before, I'm going to restrict the types of interactions between system and clock. I'm going to introduce three constraints. One is that the sum of Hamiltonian of system and clock, this should be HC, sorry, and also this one. They must commute with the interaction between system, the interaction term between system and clock. And maybe we can discuss later why this should be the case. Then I also am going to say ask for a time-independent effective Hamiltonian of the system, which means that V should not contain any terms in T, and so V should commute with Hamiltonian of the clock. And also I'm going to ask for V to contain only first-order terms in H, so that we only have first-order time derivatives, and so we're dealing with simple cases. And all these constraints exclude like some kinds of non-unitarity, effective non-unitarity dynamics on the system. So this is a very conservative assumption, so we avoid any kind of problem of such kinds. But also interactions of this kind have been considered in the literature often, and I think it's a very useful kind of interaction to consider, to study. So after applying these things, we are left with these sorts of interactions. One that is very popular is this sort of gravitational-like interaction. Effectively, this is a Newtonian potential with some post-Newtonian corrections, so we're just using the mass-energy equivalence here. So we substitute M with the Hamiltonians on each system, and we have this coupling factor here. Great, so this is kind of like a gravitational attraction between system and clock. Okay.
Sorry, I didn't quite get why we need both 1 and 2. So one is interaction commutes with the bare Hamiltonian, and the second one is with individual of them. Why do you need the second one as well?
This I just restricting to the case where V is not dependent on the time operator, on this T operator, because I want a time-independent effective Hamiltonian for the clock. Which, if we're not involved with, if we're not caring about control on the system, then I think that's a good approximation. Like the universe should be in a time-independent Hamiltonian. Okay. How do we solve? We've seen before how to quickly solve the problem with this kind of interaction. We found that this equation of motion for the state of a system is of the following kind. Now, this commutes with so this HS commutes with HS, of course, so this thing is an Hermitian, so we don't have problems with the non-unitarity here. We can express the state of a universe in this way. So psi 0 evolve with this Hamiltonian here and T. And this thing here, I'm just going to call it H effective. Okay, so we know how to do it with the zero energy eigenstate of the universe. What if we have different energy eigenstates of the universe? So what if we allow the freedom where we've seen before? So if we consider generic eigenstates of the universe. Then we do the same things as before, but just now that we have that the energy eigenvalue of the universe pops up here. So we have H minus this energy eigenvalue of the universe. And now, the crucial difference between this and before is that this is no longer a trivial energy shift. So
should it also pop up in the denominator?
No, if you do the things, no, you see that it only pop-ups there. Let's see if you can see it from here, maybe. You would have epsilon psi. Now, if you take this out here, you just have HS minus epsilon. And you see that it doesn't get into this term here. So it only pops up in the here, up here, but not down there. If you do the things as before, you see that it only pops here, not below. Mm-hmm. So this is a problem. This is different from before. So before it was only like a trivial energy shift. Now it's something more. For example, if lambda is quite big, so like we have a weak interaction, we can kind of expand this in the following way. So we have a energy shift as before, but now we also have this extra term here. What does it mean? It means that if you compare the dynamics, or like the evolution of two states of a system, which we assume the same at the beginning, but they are in different energy eigenstates of a universe. For example, their scalar product is going to behave this way, and this in general is not 1. At some point it's going to go to 0, and so on and so forth. So the two dynamics are different. There's a difference in the two dynamics. So I guess now the question is, which eigenvalue is the right one? Which eigenvalue of the universe is the right one? Can we tell if we are in the universe with eigenvalue epsilon or epsilon prime? Or can we tell from inside the system? Seeing and others here mention that this looks like a sort of renormalization kind of thing. But anyway, so I think there's a bit of ambiguity now, like which epsilon should we use? I mean, we see that we have different things if we have different epsilons. Maybe we can't tell from the system perspective inside, but which one should we choose? Like, is there a reason to choose one over the other? And I think, yeah, this is a bit of ambiguity that maybe needs to be solved. OK, but for now, like, it's not too bad. Things get bad when we have mixed states of a universe now. Because, OK, remember that we could write the state of a universe in this way. And now each of these k's evolves with an Hamiltonian, effective Hamiltonian dependent on the energy k. So what does it mean? That now, in general, this thing is no longer a unitary evolution. But we have a unitary evolution on each eigen subspace of the Hamiltonian of the universe. But they're not the same. So yeah, for example, so if you have at least 2 k's, so if you have at least 2 energy eigenvalues, in general, we have non-unitarity. For a simple example where all these rho k's are equal at the beginning, we have this sort of evolution. This is just a CPTP map with Krauss operators here, which is good, trace preserving, but it's not non-unitary. So we lose unitarity. Why is this important? Because like this state that we wrote before, to write this state, we had to span over all the eigenspaces of a universe. And now we're not really allowed to do that if you want to preserve unitarity on the system. And in general, like, you can see that good separable states of a universe would lead to a non-unitary dynamics on the system. So the message is that we can no longer encode unitary time evolution in the classical correlations with the clock if we want to preserve unitarity. And so if you want to preserve unitarity, we really need entanglement. So there's this story of entanglement that was necessary for pure states. We've seen that it's not necessary for mixed states in general. But now inserting some kinds of system clock interactions, now it becomes, again, a central thing if you want to preserve the unitary dynamics on the system side.
Sorry, but if we do not satisfy the conditions you impose, not even entanglement can save us from the evolution.
Which conditions, sorry?
No, I mean,
yes.
I violate them, then
Yeah, true.
even with entanglement pure states,
That is true.
cannot achieve.
Yeah, that is true. Yeah, yeah. I'm saying even if we restrict to these sorts of interactions, which are very non-problematic at the first glance, we still have non-unitary dynamics for mixed states of the universe. Yeah, that's another problem. Like in general, like what interactions are allowed or not. Good. So here again, an open question. So what are the consequences of this for classical relational approaches to time? Because we've seen before that we can kind of like draw a parallel between this sort of state to maybe classical states, because we just need like these t states on the clock. So what can we say about the classical relational approaches to time? So can we say something? Yeah, can we say something more about those? Can we maybe show that if we have interactions with quantum system, we cannot use a classical relational approach to time because we need these quantum correlations instead of just classical correlations. This is just an open question. Maybe we can discuss it later. But another reason, I guess why it is important that we have this non-unitarity, as again for the model I proposed before. So we have this inaccessible system outside. and we trace it out. And inside this system and clock here inside is going to be a stationary. So it's going to commute with its Hamiltonian, but in general, it's going to be a mixed state. And now we have the problem. So in general, this thing is going to evolve non-unitarily. And now this is a problem. So, yeah, it's useful to consider this kind of interaction between system and clock. OK, so now, I guess the last section. OK. Yeah, I'm going to give you a simple example about what I've talked about now. So let me consider this simple system. We have a qubit as our system of interest, and we have an ideal clock. The qubit, let's say, has an Hamiltonian like this. So there's a sigma x. And I'm just going to add, for fun, MC squared there, just like some rest energy kind of thing. Clock is ideal, so it's just the Hamiltonian of the clock. And I'm going to add the interaction we've seen before, just the Hamiltonian of the system tensors the Hamiltonian of the clock with a coupling factor, 1 over lambda. So it's a very simple model, probably one of the simplest we could do. And let's see all these things I've talked about. So let's solve this constraint. So let's solve the model. And let's recover this effective Hamiltonian of the system. So we do the steps we've seen before. We find the same effective Hamiltonian. And it's of this form. Now, usually people consider approximations where the coupling is very small. So, and then you expand this, and you get some maybe time dilation effects. But now here I'm just going to try to solve exactly because it's quite simple. And you can see that this operator here is just a phase, like a parameter phi tensor the identity, plus a parameter omega tensor this internal, let's say, internal Hamiltonian of the qubit. OK. Here are the explicit expressions for phi and omega. But what do these terms really mean? So this is just a phase. It's going to give you a global phase on the system, so it's not observable. So we're really interested here with this omega here. And basically, it affects the speed of rotation of a system, let's say. So because it's the, let's say, bare Hamiltonian of the qubit, and now it's changed by this parameter omega that will change how fast the qubit evolves or rotates. OK, so yeah, I'm going to give you just like some estimation of the non-unitarity effect I've talked about before. So I think it's interesting to see if there is this unitarity, or what scales are we expecting to see it. So it's very, very simple example where we only have two energy eigenvalues of a universe involved, one with eigenvalue 0 and the other one with eigenvalue epsilon. We assume that the state in both these eigenspaces, the state of a system in both these eigenspaces is the same at the beginning, and it's 0, 0. We solve the model. We use the equation that I showed you before. And then we find that this thing here, which in general, so it's not a unitary equation, unitary solution anymore. And in general, this term here is going to go to, I mean, the state of the system is going to go to a maximally mixed state after a certain time. And this time is given by the following expression. You can put in all the numbers and find this following expression. Another useful parameter is the number of full rotations that the qubit can do before it gets to the maximally mixed state. And it's nice because it's expressed as a term, as a ratio of the coupling parameter lambda and the difference between the energy eigenvalues of a universe. And if you insert in this lambda that gravitational kind of Newtonian potential that I showed you before, and we put the gap, the energy gap between the two eigenstates of a system as MC squared, we find that this parameter here is just the distance between system and clock, which is this one, divided by the Schwarzschild radius of the qubit. And it's funny that these kind of relativistic things pop out here. Yeah, another comment is that this is going to go to 1/2, then it's going to go back to a pure state again, 0, 0, for example. So it's not like a proper decoherence thing. But if you take more complex superposition of different energy eigenstates of a universe, you go to the maximum mixed state and then you don't come back. But anyway, this is a way of like showing, like estimating what is the effect of this non-unitarity. And for example, if you have gravitational systems, we see that this thing usually is very, very small. So us maybe on Earth, but we use the sun as a clock, we will not observe this kind of non-unitarity. If yes.
I understood that it's non-unitary, but then you said for this small simple case, there is a revival.
Yeah.
It's still non-unitary, and the revival is just accidentally.
Yeah.
Am I right?
Yes.
So
Yeah.
one can prove that, I don't know, that the purity of the states changes. Right?
Yeah.
For example, that would be a sign that it's non-unitary.
Yes. Yeah. Yeah. True. Yeah. You can do the purity in terms of t, and it goes.
You see that it goes down and then.
Exactly. Yeah. For just this simple example. But if you have more complicated things, superposition of different, more like energy eigenstates, for example, like
It stays longer than mixed.
maybe it stays long. Yeah. Yeah. Yeah.
But the effect is already here.
Yeah. Yeah. Okay, so this is just an estimation of the effect. Now I'm just gonna talk about a more funny thing that I found. And so again, we consider the same Hamiltonian as before. We have these parameters here. Just to recap, this phi is not observable, and we have this omega that determines the speed of evolution or rotation of the qubit. And now I'm going to consider different values of lambda. So how different values of lambda affect. So what is the dependence of omega on this lambda? I'm just going to explore that. And effectively, what I'm doing is looking at a clock which is a different distance from the system. So you can think about we have a collections of clock, and I'm just looking at different clocks. One is a system at distance d, one d prime, and changing the distance. So considering another clock changes the value of lambda in the equations before. So I'm not really doing a dynamical thing where system and clock are moving close to each other, because overall it's stationary. I'm just considering different clocks at different distances from the system. Okay, and so let me just plot the value of phi and omega. So what we're interested in here is omega at different values of lambda, so at different values of its coupling strength. So that's the general behavior of omega. And so let's go to the negative side, which is this Newtonian attraction kind of case. And basically, the key features here are the following. So when we go to lambda that goes to minus infinity, which means the interaction is very, very weak, we have that omega goes to 1. So basically, that's the bare speed of a qubit, or bare rotation speed of a qubit. So usual stuff. Now, as we increase the value, or like decrease the value of lambda, which means that we get the system and clock closer and closer, we see that omega goes up, which means that the qubit is gonna affect, like from the clock's perspective, the qubit is rotating faster and faster and faster. And now we have this nice feature here where at this value, this diverges. So at this value here, I mean, in this exact point, there's only a trivial solution to the problem. But as it approaches this value, the qubit starts rotating faster and faster, and the speed of rotation diverges. And interestingly, as you move across this threshold, omega changes sign. So what is the meaning of that? So my interpretation of it is that from these clocks, which are at this distance within this distance of a system, the qubit looks like it's rotating the other way, or like the way opposite to the way it rotated in the non-interaction case. So from a clock far away, the qubit rotates one way. From a clock in this region of distances, let's say, the clock rotates the other way. And when you cross this other threshold again, it starts rotating back in the normal way. What is nice is that if you put in the gravitational parameters that I've shown you before, this region of values where this thing happens, so the region of distances where this happens, is the Schwarzschild radius of the qubit. So it's around like a small, it's a small region around this, half the Schwarzschild radius of the qubit. Oops. So half here, it's probably due, I'm not sure, I need to do all the calculation, but it's probably due to this kind of like semi-classical way of treating the gravitational interaction. So usually when you have this treatment, you get this factor 2 here, but but maybe like a fully kind of relativistic treatment would get rid of this thing. And then you would have that this region here is around the event horizon of the qubit. So here is just like a way of understanding what I said before. So a clock far away from the system kind of ticks in the right direction, or like from this clock, the system goes in the right direction of time. But then when you are in this region around the event horizon of the system, the system like looks like it's evolving kind of backwards in time. And when you cross this threshold, again, everything looks normal. So here, I guess my open question is like, what is this effect? Is it meaningful? Can we find some analogies maybe, or like something similar maybe in GR? Someone pointed to maybe closed time-like curves, but I don't know much about that. But yeah, around like someone said that around this the event horizon or like around curved black holes, rotating black holes, you kind of have like closed time-like curves, and maybe someone here has more to say about this. But yeah, it's an interesting effect. So yeah, just to conclude, we have seen that. So I've shown you this Page-Wootters construction, and we've seen that if we have no system clock interaction, the energy eigenvalue of the universe is not an observable quantity. And entanglement is not really necessary on the kinematic Hilbert space. But then we've seen that if we add system and clock interactions, now different energy eigenstates lead to different dynamics on the system side, which I write here as ambiguity because, yeah, how can we choose one over the other? And we've seen that multiple energy eigenstates lead to non-unitarity of a system dynamics, which in general is a problem. And again, if you want to preserve unitarity, we need, again, entanglement on the kinematic Hilbert space. Yeah, and finally, I showed you that there's this weird time inversion effect when there's strong system clock coupling. And yeah, here are just some of the references I've used. And yeah, thank you for your attention.
My question is, can you, from the assumption that the system cannot get entangled with the clock, can you arrive at non-unitary dynamics which is irreversible?
I don't think so. I mean, in general, you have this kind of equation. So yeah, the state evolves in this way. Yeah, I'm not really sure. Yeah, maybe as Charles was saying, maybe after a long enough time, there's gonna be this revival. Or yeah, I don't know if this is irreversible. Yeah, I don't know that.
The standard version is also in the paper.
Yeah.
So I discussed with you, but just to give a kind of view for the others, that also there is a paper by Chiara and Latko in which they change the factorization of the Hilbert space between the system and clock. And so they suggest in this paper that maybe if you choose what is the system and clock, you get this kind of interaction. You have to have an interaction. Maybe you can change the factorization such that they do not interact, so it's straightforward. Okay, and then, okay, this is the question now, I think, whether the systems are integrable or not. Because this is the usual way how we solve any problem. We have interacting Hamiltonian, we go into our factorization, then we have free Hamiltonian, we solve it, we go back. Now, what I'm interested in, is there a case for which there is this, now I'm even in a most general case, not obeying these conditions, or that you have nice conditions that allow us to do everything fine in a pure case when you're entanglement. But now I think about a situation when I may violate this, and I may apparently have some non-unitary evolution. So is there an example for which the usual approach will lead to non-unitary evolution, but nevertheless, by changing this notion of the system and clock, we have a unitary evolution. We describe the evolution in this, and then at the end of the path, we go back to the to the original tensor factorization. That's one example. And the one question, the other question is related to the, what is the simplest non-integrable system for which we know that this is not possible? Usually people talk about three-body interaction or something like that. But do you know anything about that?
No, yeah, don't know much more about this. Yeah.
And about the first question, you know,
Yeah, no, I don't have any specific example in mind. So if there's a, yeah, if you can change the factorization, then so that in one, the effective dynamics is unitary, and then in the other one is non-unitary. Yeah, I don't really know. Also, yeah, I kind of prefer not changing my factorization at this stage.
yeah, and I know what it is, but I'm not even like, I do not have preference. I would just say, okay, if somebody wants to tell me, well, I want.
But there are these easy non-integrable systems in quantum chaos with like spin chain. If you add like external field, it suddenly becomes.
It is.
Yeah, and then this can be done just for few qubits, for few spins.
Well, this is exactly because the whole game with the universe and the system is usually you have two systems. So, and I know that if you have many systems, then you can get.
For many systems, you can have even the system of n oscillators, one-dimensional, and it can become, if the frequencies are like, you can write them as rational number, they're like incommensurable.
Yes.
Then you have like chaotic system, and you can have this not integrated. You cannot integrate, and it's even like for harmonic oscillators, set and harmonic oscillators.
Yes. Okay. So this could then indicate that there are cases where you cannot do that, but the game here is just two systems. That's why I'm always confused. Like, okay, if one system are not integral, is there any two-body system that is not integral?
And maybe some, because like usually like if the problem is that you could treat the whole system of spins as a one big spin, but you would have to have a symmetry. But where the non-integrability comes is when you break the symmetry. So I'm not sure. This could be, I think this could be a good problem. Maybe there are some two-body systems which are non-integrated.
Yeah. I mean, yeah, that's what the most interesting.
Like kicked tops, maybe. It's just a top that is kicked with interaction, and then it's also chaotic, so it's non-integratable.
Okay.
And it's just some interaction with actually with angular momentum.
Because that would indicate there is no way to define such an extreme.
Yeah, then.
just impose that the eigenvalues in the physical states are zero. So in these cases, at least, you have a physical criterion to tell which eigenvalue you expect, right? I don't know how much it does generalize, but at least, well, when I think of the Page-Wootters mechanism, I usually think of these constraint systems, and then the global eigenvalue is, you can derive it from some,
yeah, I agree with, yeah. Usually, yeah, Wheeler weight is 0, and that's, yeah, there's a physical way why it should be like that. But I wanted to explore a bit, like, relax this assumption and see, just from this model, what can we say? And there might be models where, like, yeah, you have the external system. When you take that out, maybe your system is stationary, but only with a different, like, your subsystem is stationary, but with a different energy eigenvalue.
Yeah, and I guess the other comment about the divergences and the weird sign inversions that you obtain for this analogies of gravitational interacting case. I should say that it doesn't sound so strange to me that at least the divergent behavior happens, and then some weird stuff happen near the Schwarzschild radius. I'm not sure how to interpret your interaction equations really in terms of redshift or things like that, but if you consider, for example, the time that you measure in infinity for the ticking of a clock that is gravitationally interacting with the system, and you approach the event horizon and make the interaction such that you're approaching the event horizon, then the redshift will diverge, and then you expect exactly this sort of behavior for the curve, right? And then, well, depending on the sort of interaction, it may just be that the clock observable is not a good correlator for measuring your system. And the case is that it diverges, or I don't know, in the case that it moves backwards. Again, just a comment, but it doesn't seem so strange to me that this sort of behavior happens.
Yeah, I mean.
Because again, practically, we explain this. I understand that if the case goes irregularly inverted, but then again regularly, like we have just band.
Yeah, for these other cases, I don't really have an intuition for. For example, if you're inside the Schwarzschild radius, then the usual time parameter t is space-like, and maybe you could derive still, at least formally, some correlations from this parameter t to the rest of your system, but I wouldn't have any interpretation for it in terms of a clock.
Yeah, that's why it's weird that it's only in this region here. Yeah, it's not in this side where you have like a change like of behavior, just like around this region. And yeah, with regard to your like integrating the time going to the event horizon, I mean here we're not really doing, like this is a static picture in the sense that here we have many clocks at different, so we're not really approaching the black hole and
but then if you consider clocks at different distances,
yes, when they behave like that, yes.
Closer and closer to the horizon, then
no, yeah, I agree. Yeah, but that's that is kind of fine with me. But yeah, this region I'm a bit puzzled by, because I mean the divergence is fine, but then this inversion here, and then again like this. I don't know. I mean I'm not an expert in GR, so that's why I hope like that someone is gonna tell me, oh yeah, this looks exactly like this thing. But yeah, thank you.
So a couple of questions that I had. Well, one of them had to do with Pavel's and Czeslav's about the non-unitary cases, basically, because they do appear in many relevant cases, including the gravitational interacting one. If you don't consider sharply localized clock, right? If you consider a clock with a quantized center of mass, and then it sort of appears an X operator in the interaction as well, and then you end up with in the non-unitary case. And they mentioned, like, at least in this qubit case, you do have this instance of purity revival, right? The purity diminishes and then it goes back again. I suppose for a system with infinitely many degrees of freedom that it may never revive, that it may just stay mixed or something like that. But my question is very elementary, and do you think that you could still do a good analysis for the system in the non-unitary case? Do you think that this non-unitary evolution is a problem? Because you can describe the global system still by the global Hamiltonian. You have the interaction. Well, you have the history state and everything. the fact that the evolution of just the partial system is non-unitary, do you think it could have any non-trivial physical consequences, for example, in terms of measurements that you do and the system? It's just something I think about.
Yeah, that's a good question. Because
it seems that all the information is still encoded, even in this non-unitary evolution.
Yes. Yeah, but I don't know, because I mean, it looks weird that you start, with the pure state, and then you lose all the coherences. Like you go to a maximum mixed state at some point. I don't know. So are you asking like if this is an observable thing on the system side, or?
Yeah, maybe if this could lead to any loss of information on the part of the system, maybe, or usually I think we could interpret this loss of coherence as stored in the system clock entanglement or something like that. So yeah, I don't know, in a concrete lab setting that you do a very simple toy model experiment, if you could expect to extract any non-trivial observable consequences of this loss of unitarity for the system.
Yeah, I don't know. I guess it depends maybe how you model things. So if you do these things there and then, you observe from an external point of view, maybe, you can see that with the system, it goes from a pure state to a maximally mixed state. Or in general, I would say that that's something that should affect your observation on the system side, right? If you start from a 0, 0, and then you go to 1/2, like if you the observer system, if you lose all these coherences, I mean, I would expect it's something observable, but I don't know if I can tell you like, oh, if this observable like changes,
like if you have this the common initial states, then it's CP map. This is like just a channel, and you can easily do a channel that gives you a maximum mixed state from the pure state. But this is like an open system, right? But then it means that something flows out. For me, the important thing to be if it's not positive or if it's irreversible, because then you could like go to somehow finally distinguish between unitarity and measurement. Because like from the separability of the state with time, you could have some irreversible operation.
Yeah, but for me,
this didn't look like it could be reversible.
For me, still doesn't sound trivial whether you can do such a thing, because usually, in this case at least, I tend to naively identify this parameter t, in which the things evolve, with an external time that a classical clock would measure, and then consider a usual classical setting to apply the classical laboratory to apply the measurements. This case, this parameter t refers just to the internal clock degrees of freedom that are interacting with the system. So it's not so clear to me what this non-unitarity would mean in terms of experiments, either of someone carrying the clock or some other external observer interacting with the system.
Oh, yeah, it's a good point. Yeah, I didn't explore much this thing yet, but it's. I mean, superficially, it looks like something should change drastically, but I don't have yet I can't tell you precisely yet what if you can observe this thing only from the system side. Yeah.
Yeah, just wondering. It's something that I was thinking about as well.
Mm-hmm.
One final question, since I'm talking too much already. You talked about this case with mixed states, that you had system, clock, and environment, and you talked about mixed states. When things are maybe entangled with the environment. But the cases that you mentioned is that the environment just evolves on its own, and it doesn't evolve neither of the system nor of the clock, right? I was just wondering if you consider cases where there is such an interaction and how the picture could change.
So if there's an interaction between these two and that one?
Yeah, the inaccessible system and either the system or the clock, maybe.
I'm not really sure about that. Yeah, here I just want it to be inaccessible and non-interacting with both, so I can trace it out and kind of like easy way without consequences. But yeah, I don't know how it changes if you. I mean, it doesn't look inaccessible to me anymore because you can get something, I don't know, you can get some info from this bit to either the system or the clock. So I don't know.
Yeah, no direct access at least, right? So just know there's some environment that is, well, probably messing with your system, but you don't have any direct access to it. But yeah, just.
No, yeah, no, yeah, no, this is just an example of how, yeah, why to consider a mixed state. But yeah, I didn't consider interactions between these things here. So yeah, yeah, but it's interesting, yeah, to look into this.